How old is the universe? As of this writing, and in case you're still attached to the modern way in which we measure the progression of life, the age of the universe comes in at about 436, 900,000 seconds old. That's about 13.8 billion years to you and me. But a group of scientists just pointed out that that number, turns out, might be wrong.
Many physicists had a heart attack when we got news Einstein might be wrong.
The estimates of the age of the universe now are challenged by physics and observation. Our current understanding of the universe suggests galaxies take time to develop, by accumulating stars and building structures through various processes. However, new observations with cutting-edge telescopes, like the James Webb Space Telescope, have revealed mature galaxies at a time when the universe was relatively young, some of which are even older than the universe itself. Their existence challenges our current understanding of the cosmos. Join us as we dig deep into how the universe might be older than we thought. Since the dawn of humanity and conscious thought, we have studied the stars to try and figure out our place in the cosmos. As the ages passed by, our knowledge of the cosmos has increased. At first, we thought that we were at the center of the universe. It was understood that all things revolved around the planet Earth, and this was why the sun and the moon danced across our horizon. At this time, the Earth was also widely believed to be flat. Sometime later, in 1514, a Polish astronomer by the name of Nicholas Copernicus distributed a handwritten manuscript titled The Little Commentary. Copernicus proposed that the sun is the center of the universe, not the Earth, and that the cycle of the sun and the moon is due to the rotation of the Earth. Copernicus's findings ultimately changed the way in which we examine the universe, as he was the first to use a combined approach of mathematics and physics with astronomy. While this paved the way for future scientists, physicists, and astronomers alike, it wasn't until the 17th century that Copernicus' theories were commonly held as fact. As scientific knowledge advanced, so our thoughts turned towards the bigger questions about the universe. Scientists began to muse on the origins of our universe and to question whether the universe always existed. By the 18th century, there were two main theories on the universe. The first was that it was in the millions of years old. The second theory, originally published in Siger of Brabant's The Eternity of the World in the 13th century, held that the universe had neither beginning nor end, it was eternal. In the mid-19th century, our ideas of the universe of the century started to radically change. Physicists started developing the first theories of thermodynamics, a branch of physics which deals with temperature and heat. The theory of entropy was established, which says that if the universe had no beginning or end, then all matter within it would be of the same temperature. This contradicted current theories, as it was well known by this point that there were great temperature differences across the known universe. It wasn't until the early 20th century that the works of prominent scientists such as Albert Einstein and Alexander Friedman established the theory that the universe couldn't possibly be in a static state, and that it must actually either be expanding or contracting. This changed everything, of course, and as such, new theories regarding the age of the universe had to be established. Thanks to advances in telescope technology, we were able to gain a deeper look into the universe. It was around this point that one of the most important astronomers of all time, an American by the name of Edwin Hubble, made observations of distant clusters of stars which were found to be other galaxies, like our solar system. Both Hubble and a Belgian astronomer by the name of Georges Lemaître proposed and proved a theory that established that the universe is in a state of expansion. As a direct result of this, we started to gain some real insight into the age of the universe. Hubble theorized that the beginning of the universe was approximately 2 billion years old. While Hubble was far off in his calculations, he paved the way to establishing a firmer idea of the age of the universe. To gain an accurate understanding of the age of the universe, a law of physics called the Hubble constant was established which measure the expansion rate of the universe. Hubble's law was a real breakthrough, as it could be used in a complex equation along with the determined ages of various galactic bodies to measure the age of the universe. Hubble was off in his calculations that determined the age of nearby galaxies, and as such, his idea of the age was much lower than has now been established. Thanks to the work of many scientists over the rest of the 20th and the early 21st century, it was finally established that the age of the universe was actually in the tens of billions of years old. But how did we arrive at that conclusion? Well, that is a long haul. The simplest and most straightforward way to measure the age of the universe is simply to look at the objects that are in it. Stars, for instance. We have hundreds of billions of stars in the Milky Way galaxy alone, and the overwhelming majority of the ancient history of astronomy was devoted to studying and characterizing stars. It remains an active field of research today, as astronomers have uncovered the relationship between observed properties of stellar populations and how old they are. The basic picture is this: a cloud of cold gas collapses under its own gravity, leading to the formation of large numbers of new stars all at once, that come in all different masses, colors, and brightnesses, and the largest, bluest, brightest stars burn through their fuel first. Therefore, when we look at a population of stars, we can tell how old it is by looking at what types stars still remain and what classes of stars are completely gone. Our galaxy has stars of all different ages in it, but the measurements of any individual star will be riddled with uncertainties. The reason is simple. When we view an individual star, we see it as it is today. We cannot see, or know, what happened in that star's past history that may have led to its present condition. We can only view a present-day snapshot of what exists and have to infer the rest. You'll often see attempts made to measure the age of an individual star, but that always comes along with an assumption that the star didn't have an interaction, merger, or other violent event in its past. Because of that possibility, and the fact that we only see the survivors when we look at the universe today, those ages always come along with massive uncertainties, on the order of 1 billion years or even more. However, the uncertainties are much smaller when we look at large collections of stars. The collections of stars that form within a galaxy like the Milky Way, open star clusters, typically contain a few thousand stars and only last a few 100 million years. The gravitational interactions between these stars eventually cause them to fly apart. While a small percentage last 1 billion years or even a few billion years, we have no known open star clusters that are even as old as our own solar system. Globular clusters, however, are larger, more massive, and more isolated, found throughout the halo of the Milky Way. When we observe them, we can measure the colors and brightnesses of many of the stars inside, enabling us, so long as we understand how stars work and evolve, to determine the ages of these star clusters. Although there are uncertainties here as well, there is a large population of globular clusters, even within the Milky Way alone, with ages of 12 billion years or more. How certain are we of these figures? It's tough to say. While it's almost guaranteed that the oldest of these star clusters must be between 12.5 and 13 billion years old, there remain large uncertainties about the amount of time required for a star right around the mass of our Sun to begin its transition into a subgiant, followed by its transformation into a full-blown red giant star. It could be 10 billion years, it could be 12 billion years, it could be some value in between. For years, many astronomers who worked on globular clusters argued that the oldest ones were 14, maybe even 16 billion years old. Today, we can reliably conclude there's a lower limit to the age of the universe of around 12.5 to 13 billion years from the stars we measure. But that doesn't pin down the age precisely. It's a good constraint to have, but to arrive at an actual figure, we'd like a better method. Fortunately, the universe gives us one. You see, Einstein's general relativity, for a universe filled with even amounts of matter and energy everywhere, and in all directions gives a straightforward relationship between two quantities, the amounts and types of matter and energy present within the universe, and how fast the universe is expanding today. This relationship was first derived all the way back in 1922 by Alexander Friedmann, and the equations that enable us to derive how old the universe must be are known as the Friedmann equations. It took us many years to measure the constituents of the universe, but we now have a consensus picture that's emerged. Observations ranging from the abundances of the light elements to the clustering of galaxies to how galaxy clusters collide to distant supernovae to the fluctuations in the cosmic microwave background all point towards the same universe. In particular, it's made up of about 68% dark energy, 27% dark matter, and 5% normal matter. This picture agrees with the full suite of observations that we have. You have to really cherry-pick your evidence very hard, overemphasizing measurements with large ambiguities while simultaneously ignoring large suites of data, to wind up with sets of values that vary significantly from this. So then, you might think that everything hinges on the expansion rate. If you can accurately measure that, you can simply do the math and precisely arrive at the age of the universe. Beginning the early 2000s and ever since, the best data we have comes from the cosmic microwave background, first from WMAP, then from Planck, and, as of July 14, 2020, from the Atacama Cosmology Telescope as well. Those values have all converged on the same expansion rate, 68 kilometers per second per megaparsec, with an uncertainty of just 1 to 2%. When you calculate what that means for the age of the universe, you get a very robust 13.8 billion years, completely consistent with everything we know about stars. But hang on a second. You might have heard, and rightly so, that the International Astronomical Union presently uses the term age of the universe to mean the time elapsed within the currently observable universe since the Big Bang. So, what about the entire universe? What can we say about the part of the universe that's beyond the limits of our observations? The short answer is, the universe might have a longer history. According to Queensland University of Technology's Dr. Michael Cowley, our current understanding of the universe suggests galaxies take time to develop by accumulating stars and building structures through various processes. However, new observations with cutting-edge telescopes like the James Webb Space Telescope have revealed mature galaxies at a time when the universe was relatively young. Their existence challenges our current understanding of how galaxies form and evolve over cosmic time. In other words, estimates of the age of the universe are challenged by physics and observation, and the universe might be older than we thought. Using the James Webb Space Telescope's discovery of highly evolved galaxies only 325 million years after the Big Bang is expected to have occurred, has led the University of Ottawa adjunct professor Rajendra Gupta to calculate the universe is, in fact, 26.7 billion years old. Gupta's new model, described in a paper published in the monthly notices of the Royal Astronomical Society, applies tired light, a theory first suggested by physicist Fritz Zwicky in 1929, to explain the red shifting of photons from distant galaxies. In current cosmology, redshift is the stretching of photons caused by the expansion of the universe, akin to the experience we have when an ambulance siren drops in pitch as it drives away from the listener. But tired light theory suggests that photons gradually lose energy over cosmic distances. Though it conflicts with observations, Gupta says that by allowing this theory to coexist with the expanding universe, it becomes possible to reinterpret the redshift as a hybrid phenomenon rather than purely due to expansion. And Gupta goes even further in the study, introducing the fundamental physics idea from English theoretical physicist Paul Dirac that coupling constants govern the interactions between particles. What does that mean? If these constants evolve, then the time it takes for the early galaxies observed in the Webb telescope to form extends from a few 100 million years to several billion years. Better put, it would offer an explanation for the advanced level of development and mass observed in the previously puzzling early galaxies. However, experts warn that extraordinary claims require extraordinary evidence. Regardless, at the end of the day, the universe is our laboratory, and whatever it reveals to us about how nature actually behaves is what we have to go with. Thus, it might be fun to explore or theorize about it. In short, the universe is approximately 13.8 billion years old, but that, turns out, might be wrong. We just need more data. Notably, months ago, a new era in astronomy began with the apparent discovery of low-frequency gravitational waves, the ambient hum of space-time ripples pervading the universe. That announcement came from a huge collaboration of researchers around the world. Groups in the US, Europe, India, Australia, and China are each working on their own similar experiments and are pooling their data together to improve the result. With evidence for these never-before-seen gravitational waves now firmly in hand, all those disparate teams are now feverishly gathering more data for a grander goal: to understand exactly where this background hum is really coming from. Many experts suspect that the hum mostly emerges from pairs of supermassive black holes spiraling together in the gradual process of merging, but it could instead come from even stranger sources that might represent thrilling new branches of physics. We're right at the very beginning of the field, says Chiara Mingarelli of Yale University, part of the US-led collaboration, Nanograv. The announcement came on June 28th from Nanograv and the other so-called pulsar timing arrays, or PTAs, which use radio telescopes to track the precise arrival time of the regular flashes from pulsars, rapidly spinning neutron stars left behind after supernovae. Using dozens of pulsars and monitoring the arrival times of pulses to nanosecond-scale precision on decadal timescales, they can discern background gravitational waves passing through our solar system. Such waves slightly shrink or expand the intervening space between our planet and the targeted pulsars, creating telltale offsets in the arrival times of pulses. The astonishing result follows an earlier epoch of discovery that began in 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, first detected gravitational waves produced by colliding stellar mass black holes and neutron stars. LIGO, its European counterpart Virgo, and similar facilities continue their hunt for these higher-frequency gravitational waves today. The evidence for a background hum of low-frequency gravitational waves comes from a total of 115 pulsars that were observed across many years by the multiple teams. Now efforts are underway to combine all those pulsar timing data into a single data set as part of the International Pulsar Timing Array, or IPTA, which will improve the data set's overall sensitivity. We're working on this together, Mingarelli says. We have one representative from each PTA working to start combining the data. That collective effort has been ongoing for 2 years already, and more definitive results are expected to appear by the end of 2023 or sometime in 2024. That is going to be the most sensitive pulsar timing array data set that's ever been put together, says Nihan Pol of Vanderbilt University. China's ambivalent involvement in joining the IPTA's efforts is somewhat complicating matters. They are not part of the agreement for this data release, says Scott Ransom of the National Radio Astronomy Observatory in Virginia. In the next few months, they may say they want to play nice with the rest of the community, or they may continue to go on their own. We just don't know. The Chinese Pulsar Timing Array team is in an enviable position because it has unfettered access to the huge 500-meter Aperture Spherical Radio Telescope, or FAST, in the nation's southwestern region. FAST is far more sensitive than any radio telescope currently in existence and twice as powerful as the Arecibo telescope in Puerto Rico, which collapsed in 2020. FAST is way better than almost every other radio telescope in the world, Ransom says. It's incredible for pulsars, period. For example, although China's PTA has spent just 3 years timing pulsars with FAST, it was still able to find similar hints of low-frequency gravitational waves that took 15 years for Nanograv to uncover. Members of China's PTA team did not respond to requests for comment from Scientific American. FAST is unlikely to dominate the field forever, though. Currently, the next best radio telescope for pulsar timing is Meerkat, a collection of 64 dishes in South Africa, which will have its own data added to the IPTA's current efforts. A 2,000-dish-strong project planned for Nevada, called DSA-2000 or Deep Synoptic Array, could be equally promising. A quarter of its time is set to be dedicated to Nanograv's pulsar timing observations. According to Stephen Taylor of Vanderbilt University, Nanograv's chair, that would be a huge boon to our science. And the upcoming square-kilometer array in Australia and South Africa, set to boast some 200 antennas by 2028, with thousands more to follow, should, at minimum, match FAST's capabilities. Regardless of geopolitical concerns, astronomers across the globe are united in their eagerness to find the source of this gravitational wave hum. By gathering and comparing the timings of more and more pulsars, they hope to start building a more detailed map of this background noise on the sky. If pairs of death-spiraling supermassive black holes are the cause, they should eventually appear as hotspots on this map. According to Taylor, it'll be a slow resolution of the individual sources over years. It won't necessarily be a single eureka moment. It's a slow burn. If such hotspots can be identified, however, then astronomers could start probing the particulars of supermassive black hole pairs. We would be able to learn how far apart the binaries are, says Caitlin Witt of Northwestern University, as well as the masses of the constituent black holes. Other telescopes might then be able to scrutinize and study the black holes' cosmic environs, potentially revealing more about the role these gravitational behemoths play in galactic growth and evolution. As Achamvedu Gopakumar of the Tata Institute of Fundamental Research in Mumbai, who is chair of the Indian Pulsar Timing Array, said, "A supermassive black hole binary picked up by a PTA will be followed by all sorts of electromagnetic and neutrino observations, and even photos of those things. That will be amazing, and that's what we are looking forward to." POL has already sought such hotspots in the available PTA observations by looking in the data for signs of anisotropy, that is, signs of variation and structure rather than formless homogeneity. Although statistically inconclusive, the results do show tentative hints of some hotspots, such as one toward the Virgo cluster, a large group of galaxies about 50 million light-years from Earth. "We do see some interesting features," he says, "but we really need more data." So far, the potential hotspots seem to correlate with regions of the sky where fewer pulsars have been used in the data sets, meaning the anisotropy may simply be a mirage-like artifact of data collection. The uncertainties on those measurements could just be so big that the potential hotspots prove to be consistent with the rest of the sky, Paul says. If, over the next few years, no anisotropy emerges, that could point to stranger things as the source of low-frequency gravitational waves. If true, that will raise a lot of eyebrows. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.